Good morning. Today we discuss inverse of a matrix or the multiplicative inverse of a square matrix. If capital A and capital B are two square matrices of the same order such that A into B is equal to I, that means I is the unit matrix of the same order as that of A and a B, then B is called multiplicative inverse of A or simply inverse of A, and B is written as A to the power minus 1. Similarly, if BA is equal to I, BA is equal to I means unit matrix, then A is called multiplicative inverse of B and A is written as B to the power minus 1. So A into A inverse, that equal to A inverse into A is equal to I. B into B inverse, that equal to B inverse into B, that equal to I. So B, that means A into B is equal to I, means B is the multiplicative inverse of A. BA is equal to I means A is the multiplicative inverse of B. Now we take an example. The matrices 4, 3, 5, 4 and 4 minus 3 minus 5, 4 are multiplicative inverse of each other, because 4, 3, 5, 4 into 4 minus 3 minus 5, 4, that equal to 16 minus 15, first row, first column. Similarly, first row, second column, minus 12 plus 12. Second row, first column, 20 minus 20. Second row, second column, that means minus 15 plus 16. That equal to 1001, that equal to I. Similarly, if we reverse it, 4 minus 3 minus 5, 4 into 4, 3, 5, 4, then we have also a unit matrix 1, 0, 0, 1. So 4, 3, 5, 4 and 4 minus 3 minus 5, 4 are multiplicative inverse of each other. Now we take some notes. The 0 matrix has no multiplicative inverse. So, in the real number system, 0 has no multiplicative inverse. Similarly, the 0 matrix, first the 0 matrix has no multiplicative inverse. Okay. In the real number system, 1 is the multiplicative inverse of itself. Similarly, in the matrix, the unit matrix is the multiplicative inverse of itself. Is the multiplicative inverse of itself. That means a unit matrix multiplied to unit matrix, that equal to a unit matrix. Number 3, if AB is equal to BA, AB is equal to BA does not imply that A and B are multiplicative inverse of each other. A and B are multiplicative inverse of each other. Now we take an example. If if A is equal to 0 to 20 and B is equal to 2002, then AB is equal to BA, that equal to 0440, that not equal to I, Number 4, the inverse of matrix A is denoted by the inverse matrix of capital A is denoted by a to the power minus 1, which is not equal to 1 by a. In a real number 2 to the power minus 1, you can write 1 by 2, but in matrix a to the power minus 1 means that the inverse of a, which is not equal to 1 by a. A matrix. Number 5, a matrix whose inverse exists. A matrix whose inverse exists is called invertible matrix. An invertible matrix. A matrix whose inverse exists is called an invertible matrix. Okay. Next we will discuss adjoint of a matrix. Adjoint of a matrix. Adjoint of a matrix. Okay. If capital A, small aij, n cross n is a square matrix of order n, then the transpose of the matrix capital A ij, of which elements are the cofactors of the corresponding elements of the corresponding element in determinant A is called the adjoint or adjugate of a matrix capital A, of matrix capital A. It is denoted by ADJA. So adjoint of adj of a, adjoint of a, that equal to capital A J I, that equal to n cross n. Okay, that means here capital A is a matrix of order n. Aij, I stands for row, J stands for columns. Small, that means element A11, A12, A13 up to A1n. Similarly, N1, N2 up to An of order n. Then the transpose of the matrix capital Aij. You know, capital A denotes the cofactor of the elements of small a. That means, suppose the element A11, that the cofactor of a small a1, we write it capital A11. Transpose of the matrix capital Aij n cross n, of which elements are the cofactors of the corresponding element in determinant A, is called the adjoint of A or adjuvant of the matrix A, denoted by Adj. So Adj is equal to adjoint of A is equal to capital A Ji. You know, transpose of a matrix means we change rows into columns and columns into rows. So we write here in place of Aij, we write a capital A Ji. Okay. Then if suppose we take a matrix, if capital A, that equal to A11, A12, A13, A21, A22, A23, A31, A32, A33, then adjoint of A, Adj of A is equal to capital A 11, capital A 12, capital A 13, column wise. These are the cofactors of the first row elements. A21, A22, A23, A31, A32, A33. Okay, this is the adjoint of A. Where capital, we writing where capital Aij are the cofactors, of small aij, cofactors of small aij in determinant A. Okay. Now we take an example. Find the adjoint of the matrix. Example. Find the adjoint of the matrix 1 1 1 minus 1 2 minus 1 2 1 3 minus 2 1 1 minus 1 2 minus 1 2 1 3 minus 2. Now we find the adjoint of this matrix. Answer. Let capital A 1 1 minus 1 2 minus 1 2 1 3 minus 2. Cofactors. Now we find the cofactors of elements of determinant A are, we denote cofactor of the first row first column element as C11. We know the shortcut version of cofactor of first row first column element, that is the plus of minor of first row first column element. Here minor of first row first column element is minus 1 2 3 minus 2. Okay, that equal to 2 minus 6, that equal to minus 4. 2 minus 6 that equal to minus 4. Similarly, C12, that is the first row, second column element, that means 1 minus of its minor 2 to 1 minus 2, that equal to minus of minus 4 minus 2, that equal to minus of minus 6, that equal to 6. Okay, you know where sum of row column is even, then the cofactor of that element is plus of its minor. Where sum of row column is odd, then they are the cofactor of that element is the minus of minor of that element. C13, that equal to plus of its minor 2 minus 1 1 3, that equal to 6 plus 1, that equal to 7. 6 plus 1, that equal to 7. Now we find the second row elements cofactor C21. Second row first column element 2, that is 2, that equal to minus of its minor, that equal to 1 minus 1 1 minus 1 1 minus 1 3 minus 2, that equal to minus of 2 minus 2 plus 3, that equal to minus 1. Now C22 plus of its minor 1 minus 1 1 minus 2, that equal to minus 2 plus 1, that equal to minus 1. Minus 2 plus 1, that equal to minus 1. Now C23 that equal to minus of its minor 2 3 1 1 1 3, that equal to minus of 3 minus 1 minus 2. C31 plus of its minor 1 minus 1 2, that equal to 2 minus 1, that equal to 1. C32 that equal to C32 is equal to minus of C32, that equal to minus of 1 minus 1 2 2, that equal to minus of 2 plus 2, that equal to minus 4. C33 that equal to plus of its minor 1 1 2 minus 1, that equal to minus 1 minus 2, that equal to minus 3. So adjoint of A that equal to transpose of the matrix, then we get C11 C12 C13 C21 C22 C23 C31 C32 C33. That the cofactor of first row first column C11, C12 cofactor of first row second column. And the value of these cofactors are, we get minus 4 6 7 1 minus 1 minus 1 minus 2 1 minus 4 1 minus 4 minus 3 1 minus 4 minus 3. Okay, this is the cofactor of the third order matrix A, the adjoint of the matrix A. Okay, now we discuss a theorem. Theorem 1, if capital A is a square matrix capital A is a square matrix, then A into adjoint A, that equal to adjoint A into A is equal to determinant A into I. Determinant A into I. Proof. Let capital A is equal to A11, A12, A21, A22. A is a matrix whose elements are A11, A12, A21, A22. Then adjoint of A that equal to capital A11, capital A12, capital A21, capital A22. Okay. Now A into adjoint A that equal to A11, A12, A21, A22 whole into capital A11, capital A12, capital A21, capital A22. That equal to A11, capital A11 plus A12, capital A12. A11 capital A21 plus K12 capital A22. 21 capital A11 plus second row first column plus A22 capital A12, A21 capital A21 plus A22 capital A22. You know that in determinant, a determinant can be expressed as the sum of the product of the elements of any row or column and the corresponding cofactors of the same row or column. So here first row first column element into the cofactor of that element plus first row second column element into cofactor of that element. So we write here determinant of A, that is the expansion of the determinant A. Similarly, you know in the property of a determinant, the sum of the product of the elements of any row or column and the corresponding cofactors of any other row or column of the determinant is 0. Here element of first row and the cofactor of a second row element. So the sum of the product is 0. So here the value of the is 0. Similarly, here also the value is 0 because here we write the element of a second row element but the cofactor of the element of a first row. So the value is 0. Similarly, here the value is the expansion of the determinant A. So we take a determinant A, then here we have 1 0 0 1, that equal to determinant of A into I. Similarly, we can find a adjoint A into A. Similarly adjoint A into A, that equal to determinant A into I. Determinant A into I. So A into adjoint A, that equal to adjoint A into A, that equal to determinant A into I. Okay. Now we take a, if a capital A is a singular matrix, then its adjoint is the product. If capital A is a singular matrix, then the product of a singular matrix and its adjoint is also a 0 matrix. Okay, singular matrix. Now you know singular matrix. The square matrix whose determinant value is 0 is called singular matrix. If its determinant value not equal to 0, then we say it's as a non-singular or regular matrix. We write a note: the product of singular matrix and its adjoint is zero matrix. The product of singular matrix and its adjoint is zero matrix. Okay, you know a square matrix capital A is called singular if determinant A is equal to 0. If the determinant value of a square matrix is 0, then we say it as a singular matrix. So the product of here we put singular matrix, the value is 0, so we get a 0 matrix. Okay. Now we find the inverse of a matrix. Next theorem to let capital A is a square matrix, then A inverse exists if capital A is non-singular matrix. That means the determinant value is not equal to 0, and the inverse is given by, and the inverse is given by a to the power minus 1 is equal to 1 by determinant A into adjoint A. This is the formula of inverse. Okay, that means if A is a non-singular matrix, then its inverse exists and it is given by A to the power minus 1 or A inverse is equal to 1 by determinant A into adjoint A. That means adjoint A by determinant of A. Now we prove it. We know that A into adjoint A, that equal to adjoint A into A is equal to determinant A into I. Determinant A into I. Since A is non-singular, then determinant A not equal to 0, we multiply 1 by determinant A on both sides. 1 by determinant A into adjoint A, 1 by determinant A adjoint A into A, that equal to I. That equal to A inverse is equal to 1 by determinant A into adjoint A. You know A into A inverse, that equal to A inverse into A, that equal to I. Here in place of A inverse we write 1 by determinant A into adjoint. So the A inverse is equal to 1 by determinant A into adjoint A. Now we take an example. find the inverse second order. We find the inverse of a second order determinant. Find the inverse of the matrix 2 minus 1 2 minus 1 1 3 2 minus 1 1 3. Okay, let capital A is equal to 2 minus 1 1 3. Now we test is it a singular or non-singular. Now determinant A that equal to 2 minus 1 1 3, 6 plus 1 that equal to 7 not equal to 0. Since the value of the determinant not equal to 0, so it is a non-singular matrix and its inverse exists. Now, so A inverse exists. Now we find the cofactors of the corresponding element of a determinant A. Cofactors of elements of determinant A are C11. You know that the cofactor of first row first column element is plus of its minor plus 3. That the minor of 2 is 3. That 2 belongs to first row first column. We omit it. Now we get only 3. So the cofactor of us 2 is 3. That means C11 plus 3. Similarly, C12 first row second column element that equal to minus of a minor. That means minus 1 minor of a minus 1 is 1. So we write minus of it is minor minus 1. Similarly, C21 second row first column element that equal to minus of its minor that equal to minus of minus 1 1. C22 that equal to plus of its minor that equal to 2 3. Okay, so the adjoint of A, so adjoint A that equal to C11 C12 C21 C22 that equal to 3 minus 1 1 2. 3 minus 1 1 2 column wise row wise 3 1 minus 1 2 3 1 minus 1 2. So A inverse is equal to you know 1 by determinant A into adjoint A that equal to 1 by 7 that equal to adjoint A 3 1 minus 1 2 that equal to 3 by 7 1 by 7 minus 1 by 7 2 by 7. This is the inverse of the matrix A. If we multiply A into A inverse, then we get a unit matrix. Okay, thank you.